First and foremost, thank you to all the sponsors who, without this, as such an open and inclusive event, would not be possible. Test-driven development has largely been dismissed by swaths of developers, and in some cases it is applied without a clear understanding of when and how to use the tools efficiently. In this session, I'll go over the origins of test-driven development, my personal approach, and how you can fully leverage its power to become a better developer. And don't forget, sponsor bingo, but maybe after this talk though. First of all, who am I? Hi, I'm Michael. I am a full-stack developer from Perth who spends most of his days working with .NET as a glorified virtual data plumber with .NET as well. I would like to see myself as an overly passionate tech nerd who can't stop getting excited about tech. You can find me under the handle Falcomic just about everywhere, where I talk mostly about coding and console modding. Throughout my career, with all the teams I've worked with, I've found that one thing to be true. If you're going to deliver high-quality software, testing your code is without a doubt the key deciding factor on if you're going to succeed. It is not the quality or the quantity of a developer that matters, but instead the discipline the team can make when they validate their code with the tests, and they can be run with minimal friction in both speed and resilience to change. Now, before I get started going over the basics of what test-driven development is, I thought maybe a bit to go over why. More specifically, why did I get sucked into the world of testing in the first place? Like most of you, I started out with a surface-level appreciation, but at the same time, a slight disdain for tests. A theoretical for us to consider. After spending a day or two on your PR, the very last thing you wanted to see at 5 p.m. on Friday was that the 60% code coverage was not acceptable to our code coverage overlord, SonarQube. Nevertheless, you work late and do some basic tests to cover all the new code, check in that PR, and head home for a late start to the weekend. It didn't help morale when you came in early Monday of the next morning and the work day, and you found a review come in for an obvious bug that you'd missed. It feels like you shouldn't have bothered staying late. Now that PR is going to take a hot minute to fix, and by then all the other developers will be busy working on their changes, so your pull request is not going to see a review until at least the afternoon. At times like this, it can feel like tests are there purely for metrics and not to make my code base any better. Not much good that test was. It didn't catch us my simple mistake. I've had my fair share of experiences like this up until the day when I was working on a new team and I had the great opportunity to work with a man called Paul. He was a seasoned veteran of the London School of Test-Driven Development, and he had been around in the London development scene during the London approach as it was being first matured. There were three main tools he handed over to me which completely changed how I approached writing code moving forward. Those three tools: red-green refactor, in which we never write a piece of code without having we never write a single line of production code that doesn't first have a failing test. Mocking, which enabled me to design everything around what I wanted to work on, not what needed to work on. And finally, adapters, the practice of taking third-party code that doesn't line up with your team's patterns and turning them into a small transition layer. With these three tools, I was handed the mundane task of writing a console app to use a third-party API to explore over a series of files and then to get the data out of them, to rearrange that data structure, and then to resort them into a new storage approach, and then to persist them. Basically a data migration project with a few bells and whistles. It was this project where I first was able to see the true power of test-driven development. Using mocking, my code would be tested before it was complete, and when I came to an impossible to mock third-party API, easy, I would just use an adapter to expose a more manageable interface. Finally, the most powerful tool and how every line of code was written. Red, I would first write a small test that I knew would fail. Green, I would implement a fix with as little effort as possible, but importantly, I made the failing test passed. And then finally, refactor. Now my new feature has got its implementation. I can take a short second or two to rearrange and tidy up the mess left over by the previous two steps. I took a small sample of our data and I flawlessly executed a validation migration. I then took a backup of prod, not quite believing the results, ran the tool and had a perfect migration. I did not have to set any breakpoints or debug any silly weird edge cases I didn't think of. No last minute restructuring to find the code wasn't quite readable. It just worked. Perfectly, no effort, only results. It was at this moment I found out what all coding could look like. Welcome to the London School of Test-Driven Development. Before we go any further, what is all this school nonsense? The schools line up with the locations in which these approaches were formed. The Detroit location came out of a C3 project, which was the Chrysler Comprehensive Compensation Project, which, to be more precise, was a payroll rewrite which was being taken on by a team of developers, including notably Kent Beck, in which both extreme programming and test-driven development by example, were based off of while this project was being complete, and was known as the origin of the Detroit School. Following the explosion of interest in extreme programming, many community groups formed and learned and implemented these new ideas. One such group was the London-based Extreme Tuesday Club. This group played a key role in helping Steve Freeman and Nat Price refine the techniques and approaches, ultimately leading to another of the most well-known testing Bibles, Growing Object-Oriented Software, Guided by Tests. This book expanded upon the Detroit School, but took a different focus. While the Detroit emphasized on combining interactions of classes into a singular unit, this approach centered on individual units being classes and mocking out those dependencies. Why would I want to pick the Detroit School? Detroit just makes sense. If up until now you've been writing a few tests here and there around all the important stuff, or at least to make the metrics look good, you've almost certainly been writing in the Detroit style. You might have been missing the red-green part, but overall you made a point to make the obvious chunks of functionality to be covered by tests and make sure they work the way you'd expect them to. Say, for example, you had some logic that might take an existing item, merge some new state, and then persist it back to the database. Well, this is a very good chance this functionality would have been wrapped in a series of nice tests that mocked out that database and replaced it with an in-memory fake that you could use to assert against in the final steps of your test method. If this is your code base now, great. You can transition to the Detroit School with ease. Just make sure to follow red-green refactor and you're basically there. Once you commit to testing every feature as you add it, you'll find refactoring comes in with more confidence. Why? Because if it's important, you'll have a test around it. And if you break that feature later on while applying fixes to those tests you wrote 6 months ago, will come back and they'll catch you before you release this broken functionality to your users. Another time the Detroit approach can really shine is when writing small self-contained utilities in which there are no side effects and you're simply taking incoming arguments and transforming them into an output based upon a set number of rules. Because of this, code carters such as the supermarket pricing example and others can be a good way to practice test-driven development in the Detroit style. From there, you will find it easier to spot good sections in your code base to treat as units for your testing. This will help guide your coding in such a way to push any required side effects to the edges of your code base. That way, they're much easier to mock. And by doing this, our tests are not only adding reliability, but they're also encouraging us to isolate complexity. One reason why you might not want to use this style of testing is the dreaded one line of code that breaks multiple test suites. When our unit under test combines multiple shared snippets of code, there is a large chance that eventually you'll be writing a new feature or fixing a bug, and out of nowhere, all your tests will start failing. When this happens, especially if you forgot to keep your red-green refactoring iterations small, or worse, you are not doing so, the instant stress of having to an entire set of suites failing can make it hard to find the code change itself that was at fault. There are workarounds for this. More importantly, you can focus on making sure your entire suites run continuously so that any regressions are caught as soon as the changes are made. If something breaks, you just Control Z on that thing, and all of a sudden, the responsible line of code is found. But this challenge is just a part of testing with Detroit. If your unit tests have many overlapping suites, you will find that you can topple a house of cards with the smallest of a mistake. Alternatively, this kind of pain can be nearly eliminated by using the London School approach. With the London School, you should never be retesting shared functionality between classes. The only thing that can break a test in a given suite is code that exists within that very class, since each test treats itself as a single unit under test. Some would argue that another reason to avoid the Detroit School, or even test-driven development altogether, is the short-term speed loss. But this only really applies to small-scale changes in existing code bases that already wouldn't cooperate with tests if you tried to write them. In the long run, though, if you take the time to write tests now, you can save a lot of headache later. As said, there are occasional cases where it just isn't worth it, so there's no judgment here. It is important to note that if you're going to migrate to the TDD approach for the Detroit school, that is by far quicker than if you're trying to switch to using London. For this reason, when jumping into an existing code base, Detroit might be the very and only logical approach. Okay, quick bias warning. I love the London approach, so it's going to get all my attention. The London school is by far much harder to sell first without experiencing it. But I can only say it's worth taking the time to try it out and see where your code takes you. And that's actually one of its biggest draws, especially when compared to Detroit. When writing in the London style, there's less of a need to think ahead about what your classes will be required to form, and instead you make your tests formed around them. Instead, you will naturally start at the origin of your feature, such as the API endpoint, and use your tests to define the structure of your class. And the first step of handling an incoming request is to validate the input. Then you write a test to assert this. It doesn't matter that the validator interface doesn't exist yet. You can just go ahead and define it. Once you have the interface that accepts this input and returns a suitable output, you can skip the implementation and simply create a mock for your new interface. You can then use assertion tools provided by the mock to ensure this validator is called, and later on in another test, you can implement the call to stub out the functionality, making it easy to set up tests that validate each unique and potentially hard to reproduce branch in your class. This process repeats over and over without any other downstream classes needing to be implemented. We instead focus purely on the branches and edge cases that we're tracking in this class. This, to most sane developers, will sound outlandish, spending multiple coding iterations working on tests that prove that obvious thing X is passed into another obvious thing Y. What exactly am I gaining? Well, what you're gaining is software that is designed in an outside-in style. I found that if I work from my code from the outside all the way in, I'm able to discover shared responsibilities much sooner, and I can invest in designing much more understandable APIs as I develop, rather than coming back and reworking them later. Because we mock every single call and never depend on external code within our unit, our entire code base remains open to substitution at any time. A great example of this is when later in the project you experience a race condition bug caused by 2 different calls to datetime.now. If we had been testing without mocks, all of our time-sensitive code is now causing us headaches, as it will be unmockable and nearly impossible to reproduce in a test. With the London approach, everything is injected, meaning anything can be mocked. I would say the final and possible most impactful tool that the London school gives you is the ability to split up your features into smaller tickets and make it a much more manageable process. I found that most teams I work with who don't use the London approach will typically find themselves having a single developer delivering an entire feature from start to end, even if a ticket is split up into multiple steps. If, say, for example, a team splits up a ticket assigning Harry to map the user input to the domain model and Chiara to handle SQL persistence, they might run into an unfortunate issue. Both developers end up implementing their own version of the same file. For example, Harry defines car info as a record. Meanwhile, Chiara implements car info as a class because they're using Entity Framework, a library which relies upon class mutation to track field updates for generating SQL queries. Their version is a mutable class, whereas the record is not. Now one of them has to rework their implementation, and neither is happy about it. This is why quite often when a team writes up their tickets, they end up turning a feature ticket into the entire ticket, rather than breaking it down into the individual steps needed to complete the feature. If instead of 6 small tickets, we had one big ticket, a single developer could pick it up, work from start to finish without running into these conflicts. But now our work is in bigger chunks, which can lead to half-complete sprints with no tickets left. This all could have been avoided if the priority was to deliver the domain models and interfaces at an earlier stage. So sometimes this will happen. A feature will have an initial ticket which defines the endpoint and also sets up a basic interfaces such as a validator, mappers, and database layer. However, because they're using testing in the Detroit style, they'll have no way to test this code. And as you implement all of these interfaces, now you're going to have a total of 0% code coverage, as we cannot write tests for code that is not implemented yet. This often leads to code that doesn't play nice with testing later, and often can make it harder to write tests around code which is already failing. If instead of not testing our important upper layer, we just instead for now mocked away all the mappers, validators, and persistence calls, well now, later down the line, if we find a bug in this layer of the code base, we know for a fact that we're going to be able to recreate the bug as a test, fix it, validate it, and have a test passing. The London approach forces us to, at all times, write code that has a failing test, and it also makes each line we write more testable. If your team is finding that their tickets are taking more than a day to complete, this is a good sign that you most likely might need to split up your tickets into smaller bite-sized tickets. That take more like about half a day to complete. It is at this point you might also find swapping to the London approach will make all of this much more manageable. Maintenance is by far the largest reason why the Detroit school might be a better pick over London. When you write 40 tests for a single class and a bunch of them are basic scaffolding tests, they don't really test much, you'll find that a simple change that refactors a clump of code out from one class into another to be excruciating to move. To do so correctly, you would need to basically fully recreate the red-green refactor cycle for all the code that's being moved, plus set up a new test that tests the old classes to validate the refactored chunk of code's interface is being called correctly. When you're simply trying to do a little cleanup, this can be burdensome and might lead to less time spent refactoring. There is a silver lining here in that it can help you if you suffer from a bit of premature refactile, but unfortunately, making it this hard to get work done can be a problem. With that said, I've noticed if I with a small bend in the rules, you can cut-paste refactor a bunch of the unit tests themselves, essentially shuffling the unit tests from one place without ever going through a proper red-green refactoring process. Another approach would be to, once a unit test is complete, go back through the suite and remove all the scaffolding tests, leaving only those that validate the extremities of the unit, and this would be the by-the-book approach to making this more manageable. But honestly, I've just always struggled to delete my tests. I want to keep all of my babies. It can sometimes be hard to know what the correct approach to take when writing tests is for your code base. Do I take the Detroit approach, which closely matches up to how developers instinctively test, or do I take a much more extreme route and allow my tests to define my API, choosing to chip away at the code one concern at a time through the isolation that mocking allows? The answer to this is everybody's favorite. It depends. However, this time we get to complete that sentence by saying, it depends on your team. One of the biggest mistakes any new developer, no matter the seniority, can make when joining a new team is to try to uproot the established team coding approach and replace it with their own. Does this mean if you're on a team and they have no real testing strategy, just a few tests here and there, that you can't improve things? No, it doesn't. What it means is if you have a team who might be open to the idea of testing, they just need a little help. What this also means is a more involved process like the London School are more likely a no-go, as the classes they've already written most likely will have landmines scattered all throughout them, the code base, which will refuse to be isolated for mocking. So you'll want to minimize your mocks and focus more on writing unit tests that cover more of an integration style. It is important to talk with your colleagues to get their feedback on how the code is being written and to provide some ideas on how it could be improved to see what works for them. Most developers know deep down they should be writing tests, but are just struggling to justify their time doing so. If you come in and help making tests the norms, you will likely find they will come willing. What this all mostly boils down to is there's a high chance you should just use the Detroit style, and even if you wish you could be writing London, which has been my reality for most of my recent engagements. If a new project is coming up and you're confident with the London approach, why not start out with heavy mocking and see how it works for your team? You can always pivot back to Detroit if this isn't working out, and by that point, hopefully, even if you do remove your London style, your code base will have already gained a bunch of clarity from the outside-in approach done so far. Now that we know about the different approaches to test-driven development, now would be no better time than ever to go back to the techniques to see how we can apply these to our coding and get some better explanations, examples of what this proper implementation can look like. Starting out with a red-green refactor example using JavaScript. It doesn't matter what type of approach you take, the test-driven development, your first step will always be red-green refactor. First, we write a test that will fail. It should be small and easy to write. It doesn't have to compile. Red can actually just mean that the code didn't even compile, or it can mean that the test status is red. The non-existence of the sum function in your test is the red step for this code. Now we need to make the test work with as minimal amount of changes as possible, all sins permitted. Was your test 2 + 2 = 4? Great, stop out the method with 2 arguments and then return 4. It does not matter that the implementation is obviously wrong. This is 100% okay. If you can look at an implementation and see that it is flawed, this is a sign that you do not have enough tests yet, and you can continue the red-green cycle until you come to a more concrete output. This approach is known as stutter testing and can quite often be used in conjunction with other approaches such as triangulation. Refactor is the key part of the design aspect of test-driven design. If you have been following TDD correctly, your solution will be as minimalistic as possible. And does the world's most understandable and maintainable code come into existence for free? Normally not. So the refactor stage can be used to make your code feel more comfortable to be checked in. In this specific instance, our refactoring is to remove the duplication between our test and our implementation, which both used for. And this is a really minimalistic example, which is why, even though this does feel a bit silly, the point is just to show, even if a solution feels wrong, if it satisfies the test, it is the correct approach. And we can use the refactor steps later to clean up and to do away with some duplication. In a more realistic scenario, quite often the act of adding additional tests will flush out these silly solutions and come to a more satisfying solution. Your test code is just as important as your production code. If there is duplication in the test you're writing, then they should be refactored once your code base is green. Apply these fixes with the same rigor as you would with your production code. Another tool that is invaluable is mocking, in particular extensive mocking. Mocking sounds like a really simple subject, but depending on how you approach it, you can get 2 vastly different results. One such approach is creating a new concrete implementation of an interface, which you will then inject into your code base that was designed purely for testing. Say, for example, you're doing a mock implementation of your database. This implementation won't be as fully extensive, but it will allow you to simulate calling out to the real database without any of the drawbacks of talking to a real database during testing. Through the creation of this mock by hand, we have also added the ability to embed test utilities such as data initialization and whatever test utility we can put our minds to. This is a common approach in the Detroit School of Test-Driven Development. By creating a concrete implementation, we will allow a series of interactions to build up naturally. For example, we might have a test that retrieves a value from the database, then modifies it, and without mocking, your next test run might actually fail because you've already changed that value. Alternatively, if we would have used a substitution framework instead of a handcrafted mock, we would have also had to set up a lot more setup code, which is why these concrete implementations can be handy. Speaking of substitution framework, in C# we have a few, namely mock, fake it easy, or nsubstitute. These tools allow for expressions to be written that get called in the place of the interface we supply them, allowing us to define inline out to our test what the call will return, or even allowing us to assert that a call was made to it in the first place. The only thing to keep in mind here is that these frameworks do have some support for classes in languages like C#. However, they are limited, and a lot of the time, a mock around a class will fail. It is for this reason that when using mocking, you should tend to also be stricter with the separation of logic and data, and also the usage of adapters so that you can have interfaces being your mocked code. The adapter pattern isn't a strict rule, but rather a way to introduce an adaptation layer between the third-party code instead of talking to it directly. This can help remove implementation details from our dependent code base. For example, an adapter might provide a getter that first sets up a factory to the third-party component and then executes it, all while keeping the interaction as a much simpler and well-aligned with the code-based getter method. It is only important that the layer remains as simplistic as possible, as it is often not viable to test it. Without integration testing, so if your adapter grows too much, you will end up having dangerously uncovered sections of code. When following the London approach of test-driven development, most use of adapters will be a lot more thinner and will be a lot more extensive than you might expect. I even always mock out my date times, which gives us the ability to test them as if they were pure functions, which lead to less brittle testing and also make testing edge cases a whole lot easier. Full control over how much time changes between each call to now, so now will now allow us to write code that tests those really weird edge cases. I will now go over a detailed example of how I think TDD should be implemented. In this C# example, I will dig into adapters further. For this example, I will use C# and the London School approach, as this is my bread and butter. With this, I'll be able to create a concrete example of how test-driven development can be implemented. I will be taking all three key concepts from today and combining them together to validate a record that is passed in and then return that result. If the validation failed, it'll also log that. To make this demo possible, I'm using the following tools: NUnit as my test runner and the assertion library, and Fake It Easy, which is a mocking library which allows for inline definitions of mocks and also provides several useful tools to validate how mocks have been interacted with. Originally, this was actually going to be live, but then I opened up my Mac laptop and remembered that all my bindings are Windows-based and I'm 100% lost. So in the interest of not flapping around like a grounded fish for the next 10 minutes, I will instead jump to my backup slides in this demo. Note to self, if I swap to a Windows machine in the future, blame my macOS keyboard. Note to self too, don't read this out aloud. Oh. First, we start with our blank unit test. This is our starting point, so now we need a red. Now that we have added in the handler, which we'll be testing, called validate car info command handler. The red phase of this cycle is the fact that this class does not exist. A compilation error is as much of a red step as a failing test is. Our next step is green, which we will achieve through the implementation of update car info handler with as little effort as possible. And that's it. Note how all I have to do to get the test green is to simply define the interface and the implementation. Next, we update our test to call the method that we'll be implementing called handle async. The only issue here is, what do we place in as the argument? In this situation, we'll be receiving a record type called car info to pass in, but how should I define this new car info instance that we're going to use? We don't know anything about car info. However, in this demo, it actually is a pretty simple record, but there are times in which a data type object can get relatively complicated to construct and require many required and optional properties. To get around this in a situation like this, we can actually use a mock in the place of the data type. This may feel, once again, a bit silly, but again, it's our job as red-green refactor raters to make sure we take the simplest steps possible to get from a failing code to passing code. This includes in our test suites. A cool thing about this approach is that even though we're using a mock, this is still a record type when we define it this way. This means that we're able to use the records with syntax to modify individual properties. In the past, I've found to construct my test records, I would have to go and I would have to generate an example request from the schema, take a lot of work to then snapshot that, record it as a data file, then read that file in and use some JSON decoding, and that would be my starting record. But now, all I need to do is write a simple little mock, and then I can use the with expression to customize it. Now that we have a failing to compile test, all we need to do is, and our definition is done, and our test will pass. We have now seen the first and second step of red and green, so finally comes refactor. If we have a look at the boilerplate test we have been filling out, we can see that some code cleanup could be completed to improve the test suite that we are working on. In this situation, we want to rename the test to explain what we're actually trying to achieve. We don't have to exclusively use the refactor step on our code implementation or on to fix the code that we're running in our tests. We can take the time to actually to tidy up and maintain our tests overall. This can come from something as simple as renaming a method or a variable, or extracting shared functionality between tests so that they can be reused. You can even go as far as extracting useful functionality from your test suites into utilities, which will have their very own unit tests themselves. That's right, you can unit tests. We won't be going this far in this example, but the world's our oyster. Up next, why don't we start writing code towards our implementation. Let's add in a new test. This will be a cornerstone for our testing suite, which we'll be using moving forward. We don't want to break our production code or our test suite. This is the good scenario test. As we add more and more tests to our code base, this one test quite often will be used as a starting point for new tests as we write them, as it will contain all required mocking setup code to achieve a passing good scenario. This test will assert that an acceptable input that we expect to this test asserts that given an acceptable input, we expect the result to not be null and to have a success flag set to true. As we move forward, we'll find that this test does need to be updated such that it will apply basic mocks required to achieve a passing good scenario test. This shared setup code can either exist in a setup method that we call at the start of each test, or it can just exist at the top of each individual test. Now that we have our failing code due to our implementation returning null, what would be the correct implementation for making our test pass? That's right. We find the solution that takes the least effort to satisfy all the existing tests, which would just happen to mean that all we do is return a new result with the object of true pass, with true pass directly in. We are taking the simplest approach because as much as we think we know the solution, as we add more and more tests to cover each requirement, the actual implementation will show itself naturally. If we were to take a bigger leap and our implementation to include more code ahead of our tests, this would leave us with uncovered functionality, even if our IDE is telling us that it's covered, which can often lead to bugs, which will have, because of our incorrect assumptions, and will often lead to rewrites of this code anyway. We have successfully gone from red-green again, which means now we have another opportunity if we choose to refactor. Again, we'll be looking into the test suite itself to see what could be improved. I can see both some duplication and some legibility improvements that could be made here. For example, the car info mock is still 100% acceptable, but what isn't acceptable is the fact that we have duplication in the repeat implementation and no solid story behind what does this even mean. This is fixed by extracting out the repeated code into a new method called getGoodCarInfo. By doing this, we are achieving two things. One, if later on we need to refine the car info model, we won't have to modify multiple tests. Instead, we just change this one implementation. When extracting this method, we also gave a clear hint to the reader about what we are constructing. We are constructing a good car info model. This makes it obvious to someone later on that modifies this good car info that now they're doing something on purpose, and that we're expecting the data to do something because of our change. By following this pattern, our test assertions are more likely to validate that the intended change has happened rather than a test passing or failing due to bad data that we overlooked. One final refactor is I'll remove the original test. Now that I'm confident in our good case, keeping the original test around no longer adds value. Our next test will be a scaffolding test. To start writing this test implementation, our new test scenario will be copying the original good scenario test. And now I add on an assertion on that mock which defines that we expect the validation method to be called. From there, I add the validator field and set it up as a fake. And once again, we have another red step in that these lines don't compile as the interface doesn't exist. This can easily be resolved by defining the interface. From here, we can now implement the solution to our failing test. To do this, we will need to inject our dependency, of which I've also updated our test to pass this into our class now. And finally, we need to come up with an ingenious solution. Not really. At this point, we still are doing the minimum effort to make this test pass, which just so happens to be that we call the method and then we do nothing with the result. I'll be skipping the refactor step and cycle back to red now. From here, we needed another test. In this one, we'll be mocking out what validate returns, such that it returns false. The syntax here isn't too important. What you should take away from this is that when a call to validate is made and any car info parameter is passed in, that we need to return false. With this change made, our new test is ready to go. We hop into the implementation and do the most logical solution. Now when the validation result is invalid, we'll get our expected false value, and when it's successful, it'll be true. Only one problem. Turns out our happy path test is failing due to our successful value is actually false. This happened because we forgot to update the happy code path to correctly validate the mock as returned true. I found that the happy case breaking upon completion of a red-green cycle is just a part of a growing test suite, and the best solution is just to amend the happy path as we go. We won't be doing any further refactoring here, but our mock setup code we just added might be worth making reusable, in which we could extract out the setup of the method into a separate method which accepts in true or false so that we can easily mock this interaction. For now, I'm just happy as it is. And all that remains in our little demo now is to add logging in for invalid cars. In our new test, we are setting up a scenario where a specific car for our value info, we are setting up a specific value for our car name so that we can test that the value is sent through. This test will currently fail because we are not calling log inside of our implementation. However, when we run the code to validate that it's red, instead we get a different error than what we expected. I know, it appears the interface we are relying upon is being used in an untest-friendly way. Under the hood, the iLogger interface actually only defines 2 methods, and neither of those are the method that we called. This is because we were actually calling an extension method. When this happens, there are only 2 workarounds you can take. You either implement a hand-rolled mock, or you expose whatever conveniences you need, or you write your very own adapter. In this approach, this time we'll take the latter approach. The first step in writing an adapter is to determine your API. Adapter pattern can be applied either as a way to tidy up a series of interactions into a more code-based friendly way, or they can just be a simple thin layer that exists to extract a testable interface, of which this is an example of such. What I've done here is gone into the implementation of the logger extension and stolen its definition, of which I've now pasted into my iLogger interface. The log adapter class may look very simple, but this is for a reason. We won't have any tests covering this adapter, which means we need to lower the risk of an implementation bug here. I have updated our test suite to now use the iLogger interface instead of Microsoft's iLogger. Our iLog interface has the same signature as the existing tests, so this all works without issue with our existing setup code. Now that our test suite is set up and our testable interface is ready to go, we can make our new test pass. And with that, our implementation is complete. One of the downsides of adapting to an iLogger was that Microsoft has chosen to expose only a single method onto its interface, but this was for a reason. There is a lot of methods that are on those extensions, and if you keep the approach of writing an adapter, you're going to have to write an interface for every single one of them. This is because, what this means is sometimes instead of writing an adapter specifically for iLogger, it can just be easier to write a hard-coded version. This will also allow us to write some cool testing texts such as tracking of scoped fields and exposing of convenience-based methods to test your mock implementation. No, I don't expect you to memorize this. You can use the QR code to look at a complete-ish version of this, or just ask me after and I can send it to you. Thanks to how flexible the state generic can be, there are some fairly gnarly casting that needs to be done in this example shown here. And there are still some flaws in this implementation, but this is roughly at the mock implementation you could get to for the iLogger. With this mock, we have access to assertions on the log level, the exact message, and every other field that makes up the log, including the template parameters and also scoped log state. The best part about all this is, if you want this mock in your very own C# project, why not take this as a take-home project? You can build your very own logging mock and use test-driven development to build it. With nothing implemented, first you'll write the is-enabled property. Next would come a test to assert that you're able to receive the latest log level, next message, and so on and so forth. With the demo out of the way, it's no better time than ever to go over what we just saw. Firstly, whenever we start out working on code, we always start with a failing test. If we are writing production code that isn't failing, then we are failing. From there, we focus on fixing on the compilation, or failed test scenarios such we can get back to a green state. The golden rule being there that we take the path of least resistance to go back to green, even if our steps feel a little bit wrong. This is the correct solution. We will simply form another cycle to deal with these problems later. Next, it would make sense to take the time to refactor. This can be as simple as renaming a test, or it could end up in code changes in production code or even the tests themselves. We took to using mocks in both to validate the internal interactions of our units and also to substitute out the results calling into our unimplemented interfaces. By doing this, we were able to exercise the app to its fullest and ensure that every edge case inside of our unit was working as expected. Finally, when third-party code got in the way of testing, we took to the adapter pattern to extract a testable interface. By doing so, every interaction with our code base is mockable, controllable, and any logic that could lead to a bug can be isolated and tested. Coming into this session, I'm sure we had a bunch of different experienced developers. From those new to testing, those who begrudgingly add the tests around all the code, and a few people who have a lot more testing experience. For those who are new, I hope this can serve as some inspiration to go looking into deeper of the concepts of red, green, and refactor. For those out here who know their way around TDD cycle but never saw the point, I hope this can get you excited in a more structured approach. Maybe you can check out Kent Beck's book on testing if you get a chance. And finally, to those who are more experienced test-driven developers, I am sure many, if not all of you, have dismissed the mocking approach of the London School. I really hope that you can use some of the concepts of the fluent mapping frameworks to advantage and give the London style another try. Thank you. Okay, and just a little humble brag. I've had about 1 hour's sleep because I'm messed up at the moment, so I'm very happy with that.
Well done, Michael. On behalf of all of us, say thank you for such an inspiring and informational talk. Here is a special gift from the TDD crew to say thank you for today. We have time for one or two questions. We've got a couple of minutes. Any questions for Michael? I can bring a mic to you. Yep. Where was the hand?
Hey, good talk, thank you. In terms of source control, do you like to make a commit for each of the stages in each of the repetitions of the whole thing?
No,
one commit for all three?
It comes down to, there might even be times where I do a lot more than that. It really comes down to, I think testing doesn't really change how I do the committing, it's just me as a person. I tend to get a bit more of functionality written out before I do a commit, just purely because that way when I'm writing on the commit message I can explain I did something useful here rather than I did a single step, I did another single step. It would be, the messages would become not very useful in the history.
Do you have any experience or thoughts on AI coding assistants and how they would work with this approach? Or
Yes, I've actually previously done a meetup 10-minute talk on doing something similar to this. I've found that what you can do is you can set up like an ahead of time prompt where you say, given this is how I like to write my test in this style, when I have this example, write a test that covers it. So I've done it before, I've tried it. It can work sometimes, but I also find that I can code it faster, so I just don't see the point. Until we get local assistants running that can do it as I'm doing it and be faster than me, I just don't see the point.
That's all the time we have.
Yep.
Thank you very much, Michael, again. Round of applause for Michael.